of the last flights out, probably. So I was looking forward my visit to Harvard today, but so I'm happy to be able to do it anyway, even in this way. So this is a simplified version of the theorem I will present you today. This is joint work with Erwan Delay, my collaborator for many papers. So the total mass of n-dimensional asymptotically hyperbolic manifolds with scalar curvature satisfying this lower bound is non-negative. Okay, so this is the simplest version of our theorem. Now, I was warned that in the audience there might be some people who are not that familiar with this circle of problems. So just let me start with a very low level with a few elementary comments. What is this all about? Well, first, this is about asymptotically hyperbolic manifolds, and these manifolds are all over the place in theoretical physics today. So that's something which is bread and butter in theoretical physics now. So they appear as space-like hypersurfaces in solutions of Einstein equations, for example. And this is, in fact, whether or not you have a cosmological constant. The simplest example is, of course, hyperbolic space itself. It occurs as a static slice in anti-de Sitter space-time. But you can also have hyperbolic metric as a hyperboloid in Minkowski space-time. Now, I'm embarrassed to say this, but again, this is part of this elementary remarks. Then the theorem involves something called the Ricci scalar, and this is a function which contains some very partial information about the curvature of a metric. So just take a metric, calculate its curvature, and out of the curvature you can construct a function and the various functions, and one of them is the Ricci scalar. And this inequality, which appears in the statement of the theorem, that the Ricci scalar is larger than a specific number, and this number depends upon the dimension. Well, this inequality is the same as saying that the local energy of matter fields is positive. In other words, if you look at this theorem in the context of theoretical physics, of the context of Einstein equation, then this inequality that the Ricci scalar is larger than a number is not always, but in many situations of interest, the same as saying that the local energy of matter fields is positive. So this is a theorem in differential geometry, but it has also direct relevance to theoretical physics. And why should one care to start with? Energy for systems.
I have a question.
Yes.
So, I mean, if you took just like in 4 dimensions and you took a massless scalar field with the wrong sign action, that would have a traceless stress tensor, so it would still leave the Ricci scalar 0. But you could make the energy density negative. Isn't it surprising that you can prove anything with such a weak constraint just on the Ricci scalar?
Well, yeah, this is, I think I get the gist of your question. And yeah. Well, first of all, the sign is a bit relevant because if we decided to count all energy negative, this wouldn't matter, right? But
well, we could have two, one with one sign and one with the other sign, and then we could make it arbitrarily positive or negative.
Right, and of course, if you just take 2 scalar fields and you take one of them has the wrong sign, the other has a positive, the usual sign, and they're all linear, then the energy is bounded from below, but then the system will be stable because the energy is conserved and it's, well, okay, it's hard. No, for linear equation, nothing will go wrong, right? So
no, it will be highly unstable. Sorry, general relativity coupled to.
No, but I'm talking about the linear equations, right? You just take 2 linear equations, uncoupled, nothing will go wrong, right? So now you have to start worrying about
you're just looking at the linear equations. Like I thought you were proving an energy condition.
Okay.
I see. Oh, okay. I'm sorry.
Yeah,
Gotcha.
I don't want to make the point that positivity energy implies stability or anything like that, because that's actually what I'm saying now. It doesn't, right? The
Yeah.
fact that energy is positive doesn't mean at all that you have any control about the dynamics. And in this particular case, well, you have this nice result of Bison and Rostvorovsky, which tells you that anti-de Sitter spacetime is not stable, period, right? So positivity of energy, even though my theorem applies to this case of Bison and Rostvorovsky, doesn't guarantee you any stability. But it can be viewed as some kind of consistency test or something like that, that the things you're doing are not obviously wrong, right? So that's the way I think about this. But this is not my main
Sorry,
point.
I still don't understand. You're proving that the energy is positive for the nonlinear system of a scalar field coupled to
That's the
gravity.
theorem, right? Total mass
Yeah.
of asymptotic hyperbolic manifolds with this scalar curvature is non-negative, right? So it's like the positivity of ADM mass, except in
But
this
then you assume,
asymptotic hyperbolic context.
but then you assume a condition on the Einstein tensor, activity, attracted, you know, the weak or the strong or the dominant energy condition.
This is
This
here,
is,
right? If you take a time symmetric initial data set or maximal initial data sets, then this condition is the same as saying that the local energy is positive, okay, of matter fields. So the energy momentum tensor will satisfy, well, we have positive time component. Okay, so if you didn't have a cosmological constant, you'd put 0 here, and that would be the positive energy theorem for asymptotically flat manifolds. Obviously, if you have such a bound, you cannot be asymptotically flat. But so this is the relevant condition in the asymptotic hyperbolic setting.
but you're only constraining the trace.
Right. Yeah, that's only about the initial data. Yeah, and this is in the context. That would be the Riemannian part, right? So that would be for maximal initial data sets. If you write down the full constraint equations, which I might have somewhere on my slides, but I'm sure you know, then this condition would be matter fields have positive energy density for initial data sets for which trace of K is 0, and have a negative cosmological constant, which has been normalized so that it's a number. Yeah. And this normalization is just for convenience to have the standard asymptotics. Good. But so why should one look at this mass and things like that other than the stability question, which is not conclusive anyway? Well, another reason is that mass and momentum and angular momentum and other global charges arise as abstractions if you make some gluing constructions. So suppose you have two manifolds satisfying some properties, you want to put them together, satisfying the same properties. These are geometric gluing constructions. There's several of them which are known now. And you can do them sometimes you cannot. And you need to understand the mass to do some of them. For example, if your gluing construction requires that the total mass is non-zero, then you'd be rather happy to know that it cannot be 0 except in very specific circumstances. Well, the positive energy theorem in asymptotically flat settings is the heart to the proof that of the black hole uniqueness for static black holes, right? So static black holes in vacuum are Schwarzschild. The heart of the proof, or an important part of the proof, is the positive energy theorem. Another reason to look at energy is another nice paper of Hollands and Waltz recently, where they show that variational identities, which involve the total mass, can be used to prove existence of instabilities. So it goes the other way around. You cannot prove stability using positivity of energy, but you can use energy arguments in some cases and with a suitable amount of technology to prove instabilities. Well, you can use the positive mass theorem to say things about the Yamabe problem. I'm not going to say anything more about that, but let me just return to the problem at hand. And the context of the theorem is asymptotically hyperbolic metrics. And well, just the simplest definition is that your metric G, which you're interested in, goes to a background metric or G bar, and G bar in this case, just the hyperbolic space metric, which in a specific coordinate system takes this form here that I'm showing you. And the total energy, well, this is the formula I like to use. You take the Ricci tensor, well, actually take the trace-free part of the Ricci tensor, that's here. You take the gradient of this funny function, and you integrate this expression over large spheres, and pass with the spheres to infinity, right? So you have a number which is dimension dependent, forget it. And now if you're thinking, what the hell does this thing have to do with the energy you're familiar with, supposing you are familiar with, then let me just assure you that this is exactly the same formula as the one you are familiar with, except that it's written in a nice form. So there's many forms to write this, and this form is more or less due to Mark Hertzley. So this is, here everything is swell and geometric, except for one thing which is not geometric in this integral, is this function v, because as I told you that this function v has to be taken square root of 1 plus r square in this coordinate system. Right? So, and this coordinate system is actually not unique, because if you make a isometry of the hyperbolic metric, then the isometry by definition will not change this, but it's going to change v. And in fact, what happens is that under these isometries, this function, which I've told you to use, becomes a linear combination of these n+1 functions, right? So in 4 space-time dimensions, a linear combination of these 4 functions. So this is a calculation you just do, and that's what's going to happen. And if you want to understand better what's happening, well, you just think about what is the isometry group of n-dimensional hyperbolic space. Well, it's essentially the same as the Lorentz group, 1 dimension higher, and it's essentially the same as the conformal group of the sphere, 1 dimension lower, right? So if we are in 3-dimensional hyperbolic space, isometries are the same as our usual 4-dimensional Lorentz group, or the same as isometries of 2-dimensional sphere. Well, not quite, up to discrete isometries. But if you think about the connected component of the identity, this is really true. And now, say, if you think about how the Lorentz group acts on this, or let me put it differently. So you have isometries of hyperbolic space. How do they act on these functions here? Well, the answer is very simple. Again, a calculation. It's the same as the action of the Lorentz group on vectors. So if you think of this as being indices of a vector in a Lorentzian space of dimension n+1, right? So n is the dimension of your hyperbolic space, so 1 dimension more. So think of this as being vector indices in n+1 dimension, then this isometries of hyperbolic space act on this as Lorentz group acting on a vector where these are the indices of this. So what does it mean? Well, it means that your total energy is, well, this definition is perfectly fine, but if you start making isometries of the hyperbolic space, you'd better do something slightly different. Well, you define not energy, but you define an energy momentum. And so this is a vector which has now n+1 indices, where you replace this function v by the basis functions of which get transformed one into another, reshuffled by the action of isometries of the hyperbolic space. And so you get, instead of getting a number, well, this number here is actually the zero component of this E is the zero component of this vector P mu. Right? And so you get these numbers. Now everything is again swell and geometric. And now you start making isometries of hyperbolic space because the V mu's change among themselves as components of a vector, then the P mu's will also change as a components of a vector. Okay. So the right setting for the positive energy theorem for hyperbolic manifolds is not about the mass, but it's already immediately about energy momentum, right? So if you're a physicist and you know about the positive energy, space-time positive energy theorem for asymptotically flat manifolds, you know that there is a positivity of mass and positive of energy momentum vector. But there, in the asymptotically flat space, in the asymptotically flat case, you can really look at them separately. Here, already at a level of one manifold, even though you don't have extrinsic curvature, you have a metric, you already have to look at the vector rather than a number. In any case, so let me just skip this. And so this is the full formulation of our theorem now. The theorem is not about the energy, but the energy momentum vector. And this energy momentum vector is time-like future pointing, or light-like future pointing, or vanishes. Okay, so this is the theorem, and under the condition that the Ricci scalar satisfies this energy inequality, if you want to. Good. So this theorem is known for 20 years if you assume that the manifold is spin, right? So this is the Wheaton type argument, which establishes that. Now the question is, what happens if the manifold is not spin? And that's the heart of what we're doing here. Let me mention that this is a completely different story if at infinity you don't have a sphere, but something more complicated. And the sign, it is known that that such a statement is wrong, and it is not known what is the optimal statement. But I don't have time to talk about this in this talk, so let me just mention this shortly. There's a nice theorem by Huang, Zhang, and Martin, which says that light-like case cannot occur here, right? So if you put this our result together with what Lam and her co-workers proved, you get this stronger statement. Time-like future pointing vanishes. Of course, it can vanish for hyperbolic space. So this is optimal now. Now, the difficult part of the proof, and the technically challenging part, is the higher dimensional asymptotically flat positive energy theorem. And this is something we just take for granted. So in other words, there are some geometric ideas, some of which I hope you will find interesting, that we present in our proof. But the core of the proof, at the end, you have to do the amazing work that has already been done by Rick and Yao and Lockham as well, just to prove positivity in all dimensions for the asymptotic flat case. So in some sense, part of our proof is a reduction of the hyperbolic positive energy theorem to the asymptotically flat one. Now, to do this reduction, we still need to do a bit of work. And there are two key previous results here. One is the mass aspect argument of Anderson, Kai, and Galloway. Maybe I'll come to this a little later if I have time. And another one is something called the masked gluing, which has been invented by Eisenberg, Lee, and Stanrov about 10 years ago. So that's the theorem, that's the background. And let me show you a picture which summarizes what's happening here. So, so you think of this as a Lorentzian vector space, and each point here is the energy momentum of some asymptotically hyperbolic manifold. So our most our proof is to show that the energy momentum vector cannot be space-like. So it cannot be outside of these cones. These are the cones of Timelike and no vectors. Futures is going up and past is going down. So we use this masked construction of Eisenberg and friends to show that the energy momentum vector cannot be space-like. Now, once you have shown that it cannot be space-like, you have to exclude the possibility that it cannot be time-like. And this is a construction which, in a lot, at heart goes to this construction of Anderson, Kai, and Galloway, which I mentioned, with some improvements that we did a little later, and also the our reduction to the asymptotically flat positive energy theorem. And finally, this yellow cone of future-directed light-like vector is due to Huang and Zhang and Martin. So I don't think that everyone is familiar with the Eisenberg-Lee-Stavrov theorem. So they prove the following. You take two asymptotically hyperbolic manifold, say with constant scalar curvature or with a scalar curvature with a control inequality or something like that. Well, the theorem is stated in this way, but the construction that can be easily adapted. So also do this for general relativistic vacuum initial data set. So you take two such objects and you can glue them together by making a connected sum at infinity. Okay, so that's the picture. This is your first, say, asymptotically hyperbolic manifold. This is the second one. Now, if you are in the asymptotic region, you can think of it has two coordinates, a radius and a sphere coordinate. So forget the radius and think of the sphere coordinates as being numbering points at infinity. So this is your sphere at infinity. So you choose 2 points n at infinity, and then you take two small neighborhoods of these points in the conformally compactified manifold. Then you can construct a third manifold, so which has the same geometric properties you started with. So for example, here the scalar curvature was -6, here is -6, then the new one will also be -6. And the difference is that you have made some, and the deformation in the original Eisenberg and company proof, there'll be a small global deformation of your metric everywhere. And of course, a big deformation here near this glowing region. But the manifold you have at the end is also asymptotic hyperbolic. And in our proof of this positive energy theorem, we need a slight variation of this result. We can do this so that we can localize the gluing. In other words, we can do it so that outside of this region, the metric has the same good properties that you started with before. It doesn't, so the metric doesn't change at all outside of the shaded region. And in the shaded region, near a small neighborhood of this gluing seam, the metric is exactly hyperbolic. Okay, so this is a small variation on this theorem of Eisenberg, Lee, and Stavrov. which we find very useful in our construction. So how do we use this? Well, we want to show as one of the steps of the proof that the energy momentum cannot be space-like, or it cannot be light-like past pointing, right? So if we go to this picture here, we cannot be in this region outside the cones, and we cannot be on the past cone either. And this goes by contradiction. If the energy momentum vector were space-like or light-like past pointing, then we use a mask-kit gluing to construct a new manifold which satisfies all the inequalities we started with, but now it's going to have the energy momentum which is time-like past pointing. So that's that's how you exclude the space-like or light-like past pointing case. And now once you have shown that it is once you've done it time-like past pointing, you need another argument to show that time-like past pointing is not possible. So let me tell you a little more about this part of the proof. So it cannot be space-like, it cannot be light-like past pointing. Just for simplicity, just assume, let's look at the space-like case, the no past pointing is the same. Well, suppose you have an energy momentum tensor, which is space-like and has perhaps a positive time component. But there's something that every physicist knows. You can use a boost to make the time component of this vector negative, right? So from the point of view of hyperbolic geometry, you're using a hyperbolic isometry, but this hyperbolic isometry acts on your vector as a boost and makes this, sorry, I'm going the wrong way, and makes this vector to have negative time component, okay? So once you've done this, this is not obvious for someone doing hyperbolic geometry perhaps, but it's obvious to every physicist that you can do this with space-like vectors. Then this is how the proof works. So this is our initial manifold, and we only look at it from outside. So this is the conformal infinity. And we make this Carlotto-Schorn type gluing to near the North Pole to obtain a manifold which satisfies all the energy inequalities we had to start with. But now, near the North Pole, in this semi-translucid region, the metric is exactly hyperbolic. Okay, so here in this region, the metric is exactly hyperbolic, a little inside the space-time as well. Okay, so that's a technical construction that we've done before. All the energy inequalities are satisfied. If you started with constant scalar curvature, you could end up with constant scalar curvature here. If you are doing this with initial data sets, vacuum, you'd also end up with a vacuum initial data set here. So now we can make a boost. Well, actually, we can make a conformal transformation of the sphere, which transforms this region, no matter how small it is, to a region which covers more than half of the sphere. Right? So just make a conformal transformation of a sphere, which goes all the way to the equator and a little beyond. Now, it's just a calculation for conformal transformations of the sphere, but we know the conformal transformations of the sphere translate to isometries of the hyperbolic metric. So there is a isometry of the hyperbolic metric which does this to you as well. And we know that these isometries of the hyperbolic metric boost your energy momentum vector. So the energy momentum vector of this new manifold will be the boosted image of the one you started with. And the boost works in the correct way if you align your things properly, so that if the time component of the energy momentum vector was negative, here it's going to be even more negative. Okay, so you start with something which has a space-like energy momentum with negative time component. You do some funny constructions which change a little your energy momentum, but if this region is small enough, then you can make sure that the new energy momentum vector is still going to remain space-like and is still going to have negative component of the mass. And then you boost it as much as you want. And you want to make sure that you go above the equator. Well, then you take another copy of your original manifold. So this thing is actually the same as this one. The orange thing at the left is the same as the blue thing in the middle. And you do a boost. However, before you're boosting, you're actually rotating it so that the direction of the space part of the momentum is exactly aligned with the negative of the original one. Okay? So now you can make your trivial ear glowing. So this is a new manifold, which the orange part is what you had here, except for a small region near this cup. The blue part below is what you had here, except for the small region near the North Pole. And here the glowing across the hyperbolic metric is trivial because you had hyperbolic metric on both sides of the equator. So you just put these things together. There's nothing to do. You just identify them trivial. Now, this is a trivial calculation for freshman vectors manipulation, right? So suppose you have two energy momentum vectors. One, M2 is such that you just, so these are Lorentzian vectors, and you rotate the space part so that there are, one is looking at the different direction, and then you add them together. Then, well, because if the mass was, well, if you add them together, first the space part cancels out, and if your initial part was negative, then the new one will be this vector, right? Now, what does this have to do with this picture? This is another calculation that you have to do. Then in this construction, the energy momentum vector of this new manifold is actually the sum of the energy momentum of this one plus the sum of the energy of momentum of this one, which was before the boost exactly the same. After the boost, it was just a rotated space part. And well, not quite, and that's why the proof is not just 3 lines, but you need to do a little more because there are error terms. Okay, so the calculation is just this. You have these two things, you put them together, the energy momenta add together, plus small error terms, and you crank the machinery. You show that if you make something small enough, then the errors will be such that you end up with an energy momentum vector which is negative. And I think it's essentially end of the proof. Now you just need to show that this is not possible, right? So this situation is not possible. And I think I was told that I have half an hour. I think I'm already somewhat over time. So I think I'm probably ready to stop here. And if somebody wants me to give some more details how this continues, I'd be glad to. But I think at this stage, I just stop here. Thank you.
Let's thank a speaker. Any questions for Piotr? So I had a question, Piotr.
Uh-huh.
So I noticed you didn't mention the rigidity case.
Uh-huh.
So I have one question, which is under Lohkamp's result from the 90s, the Hammocks paper, we know that if the mass is negative, we can make a compact perturbation of positive scalar curvature, and then we can use a recent theorem of Chow-Lee. I've drawn it, I hope it's clear, where we can embed a polyhedra in such a space. And then by his polyhedral rigidity theorem, if the dihedral angles is equal to pi over 2, which it would be if, say, I had a prism surrounding this perturbation, then the scalar curvature must vanish everywhere and I must be flat. Therefore, I cannot have negative energy. So this is a form of a proof of the positive mass theorem in the flat case. And so my question is now, given a rigidity statement for the hyperbolic case, would there be a diagram of this kind, say, where I can run a similar kind of argument, have some form of polyhedra that surrounds the compact perturbation, and have a dihedral angle kind of theorem in this case to prove a theorem like this?
So first, the Lie results don't work in high dimension yet. So
That's
presumably
true.
they would, but they are not known to be true in high dimension, and that's there are presumably severe technical difficulties where so think about the cube version of the theorem, right? When you try to make the kind of proof that Lie is doing, then you can have surfaces which start meeting the edges, and that becomes a serious problem, especially well, even in low dimensions, but even more so in high dimensions, right? So one would need to, if you wanted to use any kind of arguments like that, you'll have, so this argument works in all dimensions. Now, let's see. The energy inequality here, I have R of G's larger than a negative constant, right? So
yeah,
you cannot use this immediately at all.
No, certainly.
In this context, right? Now,
yeah,
what we're doing is we're showing how to reduce the Riemannian hyperbolic theorem to a hyperbolic positive energy theorem to the space-time asymptotically flat theorem. And this requires adding extrinsic curvature, right? So at the end, we need a version of the positive energy theorem in the full space-time setting. And this hasn't been done yet in the Lie case, right? So one would need to use mods rather than minimal surfaces.
Right, but suppose okay, so
but the bottom line is, if one did all this, then yes, and then what you're saying would just work, yeah. But that would be just a replacement of the rigidity part of the positive energy theorem.
Right. Yeah,
no,
I suspected that. Yeah. Okay, thank you very much. Yeah.
I need so here and then want to make a comment. This theorem of Eisenberg was actually known before him. We must say published a paper about it. It actually come from me about doing connect sum and several surgery on conformal boundary. Some of them
okay, that's interesting. I didn't know that. Okay.
Yeah. You should look up.
Can you email me a reference, Yao?
I have to find it, but Reeve must have published something before it. But I wrote in some open problem about how to do surgery at conformal infinity, not just connect sum, but also do surgery. So I have to find out those papers. Okay.
Yeah, I'd be glad to look at it, and of course I didn't know it before, so yeah. Okay. Thank you.
It's right after my paper that I wrote with Witten about how to construct metric with positive scalar curvature at the conformal boundary.
Okay. Okay, thank you.
Yeah.
So Piotr, just one additional question. So what I'm still not clear on is what would be the analog of Chauli's theorem, say in 3 dimensions, where I replace the scalar curvature lower bound with a negative lower bound, and I have a situation of the following kind. I have some mean curvature conditions on some polyhedra, and I want to control the dihedral angles for such a triangle. Would there be a theorem which I could then just use to somehow show that I can't have a compact perturbation of hyperbolic space, say. So that if I'm isometric to hyperbolic set outside a compact set, then I must in fact be isometric to hyperbolic space under the scalar curvature bound.
So maybe what you're saying, it would be interesting to repeat the Pauli arguments in the hyperbolic setting. Never occurred to me, and that's certainly a thought.
It seems to me that the stability part of the argument would work out, right? You just, that's never really a problem, but it kind of goes the other way. When you have something with a negative bound on the scalar curvature, you don't bound the area from below, from above, you bound it from below in terms of the genus of the minimal surface. So you would have to do something a little, you might have to do something a bit tricky. It might be.
Well, so I wouldn't say I'm familiar, but I know the ideas of this construction with when you take cubes. When you take simplices, it just becomes much more complicated. But supposing you take cubes as boundaries, then in a asymptotically flat case, you take minimal surfaces spanned, right? So here in the asymptotically hyperbolic context, you would probably not take minimal surfaces, but constant H surfaces. Of the kind you have in hyperbolic space. The angles are conformally invariant, so the angles will probably stay the same, but you should probably not take H equal, I don't know, right? But that would be the one thing to do. And so generalizing this as for say, I'm not sure how useful it is, but if you think about the fact that we don't know much about positivity of energy if you take a different topology at infinity, maybe that would, maybe one would get something interesting out of that. Right? Because you know that if the topology of at infinity is a torus, you can get negative mass. You know that if it's a higher genus and you have black hole boundaries, you can get negative mass without violating any energy conditions. So maybe such a construction would give the missing some bounds that we are not aware of in the other topologies. That sounds like an interesting project.
Thank you. Any other questions for the speaker? All right. Well,
so thank you for listening. Stay healthy. Don't socialize. Bye, guys.
Thank you very much for the beautiful talk. Thank you.
Thank you. Bye-bye.
Bye-bye.